I thank the organizer for the invitations, and it's great to see a lot of friends here. Just apologize that I got a cold, from my trip like 3 weeks ago, and I'm not fully recovered. So it means I may cough to wake you up during my talk. Just briefly, everybody probably know, right? Last year we saw these fractional quantum anomalous effect in twisted MOT2 bilayer. Here, just give you a summary of the fractional chain insular states we have observed so far. And the effect we see is robust, right? In addition to us, there's many works now in the field has seen these states, and also this FQH effect is seen in pentalayer graphene, right? And early this year, there's a work from a Chinese group kind of produce these results. So I will say at this point we have two systems, right? Twisted MOT2 and also multilayer graphene for these FQH effect. You're gonna hear more later this week on the pentalayer graphenes. So today I'm gonna focus on this twisted MOT2. Just quickly, we know twisted MOT2, once you have this AA stacking and with little twist, we have this honeycomb lattice structure. And within single unit cells, there's two energy degenerate point. We call B and C. They form these honeycomb lattice. What's important is pointed out by Alan and Feng Chen is that these honeycomb lattice actually they have this layer pseudo-spin skyrmion texture. This gives rise to these twisted MOT2 as a platform to create these Kavli models, and we have a flat, basically chain band in the top of valence band. So my colleague Matt, he studied these twisted MOT2 using scantality microscopy and spectroscopies. So I just want to highlight that if you look at the topographic image, you can image these XM, MX, and MM sites. These MX and XM form these honeycomb lattice. If you image the states from the K-valley flat bands, you can indeed see the denser states localized at these MX and XM. So this is consistent with the understanding. And we have done many different ways to probe these fractional chain insular states. And the first one I show you is we use called tryon sensing. Basically, we look at the photoluminescence of the tryon states in twisted MOT2. So the key, what I show you here is a PO intensity plot as function of filling factor in the vertical axis and the photon energies. So you can see that there's the fractional fillings like -3/5, 2/3, the integer filling -1. You'll see the suppression of luminescence intensities as function of the filling factor. That's just due to the formation of many body gaps. So use that. We can map out the Venn diagram, use these optical measurements. So what I show you here, right, the top is the data as function of a magnetic field. The color plot represents the PO intensities. These dark line represent the suppression of the PO intensities, correspond to these chain insular states. In the bottom, right, we extract the depositions of these states and compare with the Strata formula. These just give us the thermodynamic evidence of these chain insular states, right, or either integer or fractional ones. And we can take another step forward, just take a derivative of these PO intensity plot as function of filling factor. This gives us enhanced the contrast, and we can see additional states from these previous data, right? For example, there's another one more for -4/7. So in addition to these optical measurements, we also perform the transport measurements in twisted MOT2. And what I show you here on the left is the longitudinal resistance RXX as function of filling factor in the horizontal axis, and the vertical is the electric field. On the right-hand side is corresponding RXY. So there's a lot of information in this plot. What I emphasize is that, right, look at the RXX plot. The color scale here, the blue means vanishing RXX. Red means a very large RXX on the order of 100 kiloohms or more. And the black just means it's too large to measure. So at the filling factor -1, right, there's a pocket, you see RXX suppressed, and a very strong RXY basis quantized at the edge of E square. So that's my quantum anomalous state. And at the fitting factor minus 2/3, we have these suppressed RxX, and with enhanced RxY, about 3/2 HV squared, so that's the fractional chain insular state. And between -1 and minus 2/3, there's a pocket of suppressed RxX with also suppressed RxY. And RxY here is on the order of a few kilo ohm, so that's the ferromagnetic metal phase. Then there's another interesting feature near -1/2 fittings. You see RxX is suppressed, but a very large RxY. And this is the putative composite thermal liquid phase. The other interesting feature I want to point out is if you go around these vertical axis, once you apply the electric field, where you see these, there's sharp transitions from these near vanishing RxX to very large RxX. So that highlights the phase transitions from these quantum anomalous state to a Mali insular state. And a similar can be observed in these fractional state and also at these putative CFL state. So this highlights these electric field-induced phase transitions. And the other feature I want to emphasize is that the phenomenon we see actually is not too sensitive to the trace angles. So far, for example, for the quantum anomalous state, right, has been seen from trace angle 2.1 degrees and to 4.2 degrees. So there's a large range of trace angle for the effect. Here, just show you 4 different devices from 3.5 degrees, 3.7, 3.9 to 4.2 degrees. But the plot is RxY as function magnetic field and with RxX on the top. You can see more or less the same, right? You see the quantized RxY, the zero magnetic field with nearly vanishing RxX. So that just highlights these robust quantum anomalous state. The other thing I want to highlight is the energy scale of the state we see is large. So here I show you the temperature dependence of RxY and RxX of these minus 2/3 FCS state, right? From the top to the bottom, we have these from 100 millikelvin all the way to 3 kelvins. So even near 2 kelvins, right, the RxY is still nearly quantized with suppressed RxX. So on the bottom, I just highlight these RxY as function of temperature. So you can see RxY basically saturates below 2 kelvins and all the way to 100 millikelvins. So later you're going to hear from Long, actually, they also see the RxY actually can change as function temperature, right? That highlights the phase transitions from these FQH effect to these extended quantum anomalous state. So we don't see it actually in our device. So the effect also can be seen in many different techniques. One is I highlight the work from Andreas' group in collaboration with us. They use these nanosquid to measure these fractional chains of state, right? Because the local probe, so you can see many more states than what we see in the transport. You can talk to Andrea more for this work. The other one is you're gonna hear later today from Judy. She's gonna talk about the local probe, this box state, also in twist MOT2. I'm not going into details. It just highlights that you can also see these fractional chains of state use local conductivity measurements. Sorry for the break. So, I'm gonna take a water break. So far, everything I talked to, right, these FCS states, when the fitting factor is larger than 1/3, they more or less, right, in the first chain band and behave like those states in the lowest anomalous levels. So there's a lot of experiments and the theory kind of support these understandings. Now the question is, can we see more? If we compare if we look at these quantum hot physics, right? We know that the n equal to 1 on the levels, for example, can give you an exotic state like these 5/2. So the idea is whether we can create flat chain band to mimic the n equal to 1 on the levels. So there's a few theory works to suggest it's possible for high energy chain band, you can mimic these n equal to 1 on the levels. And so we start to look at these high energy flat chain band. Here I'm going to tell you focus on the second chain band. So on the left panel, what I show you is magnetic circuit diaprism measurements of these twist MOT2 for this particular sample is 3.7 degrees. So what I highlight here is that with this phase space, the MCD signal is finite. This just highlights the ferromagnetic phase, okay? Now we're gonna extend the measurements to higher filling factor. And this data is taken from a twist angle of 2.6 degrees. And you can see that for the phase space near -1, -2/3 is very similar to 3.7 degrees. And then we extend the measurements all the way to filling factor -3s. So you can see that there's a large phase space centered around filling factor -3 with a finite MCD signal. This just highlights that in the second chain band, we also have these interaction-induced ferromagnetisms, which is great. Then we look at the temperature dependence of all these states. For example, right, I can skip this one, but let's just focus on temperature dependence. For the at -1, you can see the Curie temperature is about 8 to 9 kelvins. And for the -3, the Curie temperature, right, if I look at the hysteresis from 2 Kelvin all the way to 6 Kelvin, from bottom to top, you can see the Curie temperature around between 5 to 6 kelvins. So this just says that the state at the -3 is also robust, but slightly weaker compared to these -1 state. So the take-home message is there's indeed ferromagnetism at the filling factor -3. Now we look at the transport measurements, right? What I show you here is RXX measurements as function of, again, right, filling factor in the horizontal axis, and the vertical is electric field, and the right-hand side is corresponding RXY. So you can see that there's a kind of suppression of RXX, but it's not zero, right? They're still finite at the filling factor -3. And then there's an enhanced RXY. But this RXY is also not quantized. So this just measurement basically correspondingly where we have a dip in RXX with enhanced RXY, it suggests that there's a putative chain into the state, but it's not fully developed. And the other key information I want to highlight is that if you look at these RXY data, the filling factor -1 and the filling factor -3, right? RXY has same color, just means that they have the same signs. So it indicates that the chain band, right? The first chain band and the second chain band, the sign of the chain number are the same, okay? So that's what these data suggest. Now if I look at the sample, right, from these 3.8 degrees, and I look at now I look at delta RXY, which is the difference of these anomalous signal. Now I want to highlight is from filling factor -1 and filling factor -3. You see that these anomalous signal actually change the signs. Right? So this just says that now the chain number for the first band and the second band, they have opposite signs at these 3.8 degrees. So we can further understand this data, just look at the Venn diagrams. So first I highlight the data from these 3.8 degrees. The top is RXX, bottom is XY. All right, you see that there's a dip developed at the high magnetic field. And if we just extract the slopes, you will see that the state at the filling factor -3 is a slope with 1. Basically, it's a chain that developed a high magnetic field. You can also see that at the line cuts at the 8 Tesla, where you see RXY is basically nearly quantized with the suppressed RXX. The key thing is that the slope is exactly opposite to the one at the filling factor -1, right? So they have opposite signs. So if we do the same thing for the data for the device from 2.6 degrees, now we can see that the slope at the filling factor -3 now is at the same sign with the one at the filling factor -1. So both of them basically -1s, okay? So if you want to summarize this, I just refer to my colleague D. Xiao's paper, right? They calculate the band topologies for the first and the second Moiré band as function twist angle. So I took these two plots. One is 3.89 degrees, the other is 2.45 degrees. So So you see that for these large triangle, right, the first band and the second band, the chain number has opposite signs, as we show. And then you look at these small triangle, the first and the second chain band, now they have the same sign, both are -1. We can further support this understanding by look at this little corner near filling factor -2. So this little corner, you can see that the first way, there's at the high magnitude, you see there's sharp phase transitions, okay, highlights by the sign change of these RXY, and also the change of this resistance. But at this little corner here, the RXX actually vanish with quantized RXY. So at least just line cuts at the 13 Tesla, you see that these RXY actually quantize the chain number 2 with RXX vanishes. So this tells us that there's a translator with chain number -2 developed at a high magnitude. So how do we understand this data? If we look at the simple band diagram, right, at the 0 magnitude, at the filling factor -2, so both the top valence band in the K and the -K value are occupied. Then, because the K minus K, right, they have opposite chain numbers, then the state itself is with total chain number 0. So if we increase the magnitude, so what's happening is that this magnitude, the band, right, is K value and the -K value, they have opposite spins. Therefore, they're going to shift in opposite directions. And then we saw these, the magnitude induced, right, band crossing between the bottom of the band, the second mini band of the K value, to the first band of the -K values, okay? So once these band crossing happens, you see there's a phase transitions. Then now you can see that once this band transition happens, the top two of the valence band all coming from the K value, they're isolated. So you can see the chain number actually just -2 now, right? So that's exactly what we see. Okay, so there's another feature I want to emphasize is that the filling factor -1/2, we actually see an insular state. And the state itself doesn't have dispersions. So basically saying that at the half field of flat chain band, at the 3 half fillings, we see correlated charge orders. And we know that recently there's many interesting theory predictions of a possible non-abelian state of 3 half, but we haven't seen it in these 2.6 degree samples, so you need to go different twist angle probably. Okay, so I want to compare the results. I think the result itself in twisted MOD2 is sort of generic in twisted TMDs. So the first result I compare is from these Bern-Feldman's, right, SET measurements from twisted bilayer WAC2 at a very different twist angle. But feature I want to highlight is that you see, right, these just incompressibility measurements, the vertical axis magnitude, horizontal filling factor. But you can see that as function magnitude, right, you see there's a phase transitions happening. Okay, so I think this is very similar to what we see here in the transport at the high magnitude. This is probably just band induced, you know, magnitude induced by the crossings. The second result on compare is from recent transport measurements in twisted bilayer WAC2 at the 4.2 degree. This is from the collaborations of Corey, Lei Wang, and Abai at Columbia. So what they see is the filling factor, once you go very high magnitude at the filling factor -1, there's a recovery entrance of these insulating state. They call these icing excitonic insulators. So the explanation is that the sufficiently high magnitudes overlap of electron pocket of spin value up with the whole pocket of spin value down subband can be realized. So even though we see it the -2 here, right? But that's exactly the picture we're using. So the two bands, right? You know. So what I'm saying is that there's a possibility of this state has shared the same nature of the state as seen in very high magnitudes of just WAC2. But that's just speculations. Now I'm going to make third speculations. So there's a lot of interest right now in these anomalous Hall crystal. Basically, you see quantized Hall effect, but with translational symmetry breakings. There's a lot of theory in these directions, and it highlights the recent experimental progress in these directions. You're going to hear more later, right, the talk about this topic. But I want to go back to highlight the data we have. So what I show you here is just RxY as function filling factor. So one thing I want to pay attention is that the very low magnetic field. As I increase magnetic field a little bit, you see there's a dramatically enhanced phase space for these RxY. So the bottom just line cuts of this data. The blue curve is 100 millitesla. The top of the red curve is 3 Tesla. So you see that as I increase at 100 millitesla, right, the phase space for these quantum anomalous hot state is stopped around 1.1, 1.2. As I increase magnetic field a little bit, actually, you see the phase space basically dramatically enhanced, can go to 1.3 to 1.4. So this effect is robust. We see in many different devices, and there's a strong twist angle dependence. So this effect actually, I don't know what it is. I'm looking for help. But I suggest is that there's a possibility, well, it could be another kind of anomalous hot crystals, right? As we increase the magnetic field, somehow the filling factor, the phase space just continuously, expanded. Okay? But you can tell me what it is. Yeah, I'm looking for suggestions. So lastly, hopefully I have 5 minutes. I'm going to touch upon these more than 5 minutes? Yeah. I'm doing really well. 9 minutes? 9 minutes. Good. So I can slow down a little bit because I got a warning, you have to finish everything at the 30 minutes. And I'm going to tell you these 2.1 degrees. So last year, right, I think around October, November, right, when the paper submitted, and my colleague Disha and Ting Chao, they told me that there's something interesting about the second chain band of the twisted MOT2. So here highlights what's interesting. I show you the average density of states of the band, right, as function of the twist angle. So you see the density states of the first band, they peaked within a range of twist angle between 2 to 3-ish, right? They're large. So there's no match angle. But if you look at density states of the second band, actually there's a match angle near 2 degrees. So he is very excited. He told me I should work on these 2.2 degree-ish samples. And we made many samples, but none of them worked because of the small twist angle, all the samples just relaxed. Then there's a really interesting work from the Cornell group. They managed to make 1 samples in transport. Transport device is really hard to make. And the interesting evidence is that there's a fraction quantum spin Hall effect, right, in these bilayers. I think that there's something really exotic what's happening here. For example, they see these nearly quantized RxX at the filling factor -3, but also RxY actually vanishes. Okay, so that's this work actually stimulates the community, right, especially for the theory community, to go really figure out what the state of these. So there's 2 camps. One is assume the state has time reversal symmetries. Then there's many different interesting ground states being proposed. And there's another camp suggests that the state actually has a time reversal symmetry breaking. Then there's many different other states being proposed. And I would say it's a pretty wild field. And then I told my students, probably we should stop making transport sample because it's so hard to make. Let's just go back to the optics because we know how to do it. And let's look at whether the state has ferromagnetism or not. At least we can help the theorists to confine in one direction. So that's the sample we have. So we have these sample at the 2.1 degrees. Then we perform these magnetic circuit dichroism measurements at the 0 magnetic field. Again, right, the data quality is not superb because the signal is small, but you can clearly see that there's ferromagnetism at the filling factor -1, and there's also ferromagnetism at the filling factor -3. We can enhance the signal to noise ratio a little bit, just apply 50 millitesla to suppress the reason the noise is coming from when we sweep the gate is 1.6 Kelvin. The issue is that when we sweep the filling factor, there's some magnetic fluctuations. So it gives rise to this noise. But if I use apply the magnetic field, then we can suppress all these fluctuations. Now you can see clear, right, the signal at the -1 and the -3. So we can further confirm this effect, this magnetism, by looking at the hysteresis Right, on the right-hand side, we measure MCD as function magnetic field. You see a clear hysteresis, and the same thing can be done at the -3. You see a clear hysteresis. So there's no doubt, I think there's a ferromagnetism at the filling factor -3 for the trace angle at the 2.1 degrees. We can further just extract these delta MCD means the pure, right, the hysteretic component as function filling factor. So you can see where the magnetic phase space, right? There's a large phase space at the filling factor -3. There's a ferromagnetism. One interesting phenomenon I want to emphasize is that the filling factor -1.5. There's a robust ferromagnetism. We know that for twist angle 3.7 degrees, the ferromagnetism actually stops at the filling factor -1.2, sorry. But it's not the case for the twist angle 2.1. The ferromagnetism can extend all the way to phase space beyond -1.5. So this suggests actually there might be something interesting there in 3 half fillings at the smaller twist angle. So we can also do these electric field dependence on the top, right? You can see that the ferromagnetism just can be controlled by electric field. The bottom is a temperature dependence. You see the ferromagnetism at the filling factor -1. Now it's 5 kelvins, and the -3 at the 3 kelvins. So it's very weak ferromagnetism compared to the large trace angle. And this is very easy to think about, right? Because once you reduce the trace angle, the Moiré inner shell gets larger, then the carrier density, right, becomes smaller. Also, the separation between carrier becomes smaller compared to a large trace angle. Therefore, all the magnetic interaction just become weaker. That's exactly what we see, right? The carrier temperature basically drops. So last, I'm going to show you a little fun thing we got several weeks ago. We're still trying to see if we can see what's going on. What is state? What nature of the state? We cannot make transport sample, but let's just go back to optics. We measure these transluminescence at function magnetic field, and hopefully we will see features, right? Either they disperse or don't disperse, as we first did for these 3.7 degree, how we observe these signature of a fractional chain later. So we did these measurements for these 3.1 degrees to enhance the contrast. The data I show you here is a derivative of PL with PL intensities with respect to the filling factors. So this is just the data. I haven't done anything to it, but you can see there's features here, right? There's dispersion features. And there's this feature bright, which doesn't disperse, but there's another dispersion feature at the high magnetic field. And there's something suspicious going on here. Now I'm going to make my speculations. You can, do whatever you like. But this -1, I'm pretty confident. This equal to 0 at low field, I'm pretty confident. That's basically similar to the 2.6 degree I showed you. And this is a C -2, I'm pretty confident. Very similar to what basically the same as we see at 0.6 degree. But there's a thing we're seeing here, I don't know what it is. You can see this looks like dispersion. That's a feature, but the data quality is not good enough to tell. So I'm going to stop here. So I think we're still working on this, trying to address this mystery, what is the nature of the state of filling factor -3. What I can tell you is that the time reversal symmetry breaks. That's number one. That's very confident. The second thing I'm not confident is whether this state is dispersion or not. Okay, so that's still remain work in progress. Lastly, I'm going to show you this phase diagram. I think there's a lot of interesting things going on in this twist MOT2 beyond what I told you today. And the horizontal axis I show you here is the filling factor. The vertical axis is the twist angles. So you can see that in this phase space of filling factor twist angle, there's many different states we can see, right? I'm not going to go through all of them, but the interesting thing is the -2, that could be quantum spin Haas. And some filling factor -4/3, that could be a fractional topology insulator, as recently, there's work on this group showing that. Then there could be some kind of exotic state at the 3/2, and also -3 is still all the work remain in progress. And we're probably going to see more in the next 3 to 6 months. With that, I'm going to thank all my collaborators who help us did all this work. Right, from the theory side and from the different measurement techniques like MIM, right, from nanosquid, STMs, and also HBN, crystal, etc. Especially, I like to highlight these 3 students who did the most work I talked to today. And Jiaqi is now just moved to MIT. Eric is probably on a road today to France. He's going to be a postdoc there. And Jun is graduating next year, so he's actually actively looking for postdoc positions. And he's superb. All right, thank you for your attention.
Thank you for the very nice talk. And yeah, we have now some time for questions.
Hopefully I'm on time.
Yeah.
Good.
Perfectly on time. Okay.
Hi, thanks for the nice talk. So I had a question about the first part of your talk where you were talking about the Chern number of the second band switching with the twist angle.
Yeah.
So in order to deduce that, you had to assume that the electrons were always going in the same valley, right? Because the other valley has the opposite Chern number. Is this just because of the spin-Zeeman effect, because of spin valley locking, or something else?
It's not because that. The detail is given in this paper, but the key idea is that the simultaneous number is determined by the local Moiré potentials. And in this twisted system, the local Moiré potential is determined by the 2 factors. One is the charge transfer between 2 layers. The other is in plane, there's a strain gradient, give rise to this piezoelectric effect, also modify the Moiré potentials. So now you can see, right, in a large twist angle, imagine, right, if you have a really large twist angles, when there's no lattice relaxation, then these in-plane piezoelectric effect not going to play a role. But if you go smaller twist angles, if the lattice relaxation becomes stronger, then this in-plane piezoelectric effect becomes stronger. So they actually competing with this charge transfer. So this gives rise to the change, the sign of the chain band.
Right, so that part I get, but also there are still 2 valleys, right, which have opposite Chern numbers.
Yeah.
So when you are showing the data which shows that, you have different signs of the Hall effect, for example, at 2 different twist angles, like it could be because the electrons went to the opposite valley.
It's not an effect, because you can also tell for example, the MCD, the sign hasn't changed.
Okay, I see.
And you can see the polarization of the light, for example, hasn't changed. So that tells us where these carrier coming from, which valleys. So we can basically tell, what the locations of these carriers in what the valleys. Yeah.
I see.
It's not the effect you're talking about.
Okay. More questions? Yeah.
So let me press you on one point. What is the evidence at -3/2 of a non-abelian state, besides, some theoretical papers that don't take into account many things?
Thank you for the question. So I can go back to my slides to emphasize this point. The point I have is we haven't seen any evidence of non-abeliance. We see a charge order state is favored of these predictions, but it doesn't mean the prediction is wrong, because we had these particular twist angles, and we know that all these affect strong twist angle dependence. Yeah.
But at 2.1, what is the evidence for? So the predictions, because I know them well, they were made for 2.1, and they don't take into account many things. For example, the 2-harmonic model, which we know from Dishao, is completely wrong there. And their state has large N of K fluctuations and is not a non-abelian state, the theoretical predictions. So, we can just put that aside. So experimentally, I'd like to know what is the evidence at 2.1.
I don't have evidence, but there's something suspicious, I can tell you. I was going to tell you.
I agree there's something that's super interesting. I'm asking for it.
I just don't know. Okay. Yeah. We can talk in detail. That's my plan, actually. I want to bring your attention to that.
Thank you.
Yeah.
Is there any way to get any insight about, why 2.1 is different from 2.6? Like, should we be all in the business of scanning 2.1, 2.2, 2.3? Is there any way to understand what's going on?
So theoretically, I think that's the exact thing I'm showing you here. So the calculation shows that the average DOS is peaked.
Right, that's a calculation that comes out of computer.
Yeah, that's
Do we
right.
have any insight into what's making this peak?
D, do you have any insights? I do. I have probably 10 collaborators in this room, so any question you ask, you can address it. Yeah, please answer this one.
Yeah, so basically what we find is there's a very strong twist angle dependence in terms of those Canadian model parameters. Like, when people think about the graphene, because there's only one magic angle, you don't really think about the twist angle dependence, but here you see there's a wide range of phenomena that's really twist angle dependent. You can go from very dispersive band at 5 degree down to very flat band at a 2 degree. And one of the so the main reason is because in TMD, the monolayer breaks inversion symmetry, so it becomes piezoelectric active. So we all know when you have a twisted structure, there's a lot of lattice relaxation. You see the beautiful pattern of strain. In graphene, it does almost nothing, just shrink the domain size. But in TMDs, it gives you an in-plane piezoelectric charge, so therefore give you a long-range modulation of the Moiré potential, which was not in the local stacking approximation. And that drives the band dispersion changes very drastically as a function of twist angle.
Maybe just a follow-up on that question. I mean, what is the sample dependence? For each angle, is it, can you consistently create the same behavior, sample to sample?
Yeah. So
or is it also varying sample to sample as you vary the twist angle?
When you tune the twist angle slightly, the phenomena will change slightly, but they change it very systematically. So I had a slide, but I deleted. There's a very beautiful twist angle dependence from all the way to 2.6 to 4.8.
So can you pull out something like this?
The thing is, I don't measure bandwidth.
But
I cannot extract the bandwidth.
SDM or something.
Then that's I have a colleague there. He's actually actively doing that. But that's a challenge. Yeah.
Thank you.
But is there a signal that looks like it has dependence like this, for example, the strength of the magnetism?
I don't think we can compare. For example, what I can measure, right, is magnetism. And also, but the magnetism itself, like I told you, it has a strong dependence on the thing exchange, the separation between carriers. So that doesn't tell you this. Make sense?
But is there any trend you see in the magnetization?
I cannot tell because, like I say, the magnetism actually gets weaker and weaker when you go to smaller trace angle, right? The thing is, I cannot give you information about this. So there's no direct comparison I can do. Yeah.
It seemed like you could get a twist angle dependence of the Curie-Weiss temperature. Can you see that systematically?
It just gets smaller.
It doesn't go to zero like some critical property or some critical phenomenon?
We haven't seen it. We always see is always ferromagnetism, right? So I told you the Curie temperature. Let me give you an example, right? Says 3.7 degree is 14 Kelvin. 2.6 degree is 9 Kelvins. 2.1 degree is 6 Kelvins.
It's squiggling, right?
Yeah, just keep going down. But we haven't really fit it because we don't have enough data points.
Very interesting to consider that.
I have a question about the slide. I think it was called anomalous salt crystal question mark. So it showed something that happens to RXY, that it becomes wider and wider in phase space. What happens to RXX?
Yeah, so RXX just go to 0. Yes, the same.
And it also becomes wider.
To become wider. Yes. It's in the plot here. Yeah. Let me show you. You see that, right? Yeah, here. Basically, this is RXX. This is RXY.
Thank you.
And this effect has a very strong twist angle dependence as well. Yeah.
So just to close the loop between you, Una, and D, so can we make a statement that at low angles, the experiment matches these ab initio, and that these ab initio doesn't match a 1 harmonic or a 2 harmonic model? You need larger number of harmonics for small angles, just as a community to get to some sort of a closure and not use a one harmonic model for low angles, can we make a statement that what I said is true or not? Higher than 2. And you wouldn't be able to match the Chern numbers with the 2 harmonic, actually. We checked that, actually. It's a rhetorical question.
Any more questions? Actually, I have one question about the field-induced Chern insulators.
Yeah.
So the picture you presented was kind of a single particle picture, but I should think that this is mostly an exchange effect. Or you're thinking it's really a single particle effect, just the Zeeman is big enough that it really pulls apart the bands.
So what I'm doing now is a single band. I think it's enough to explain what's happening at here, for sure. But it's not enough to explain what's happening. For example, exactly at the -2, you see there's an insulin state, right? Appears. That's just, I don't know what it is, the nature. That's how I was referred to our best paper. Then the second thing I think is very interesting, definitely I think a strong correlation effect. You see there's a phase transitions. And the field is field effect dependent, but you can see that clearly there's an insulin state appeared. Right? So that's the correlation effect. Yeah.
But how big is the Zeeman? Well, here there's kind of a valley and spin Zeeman, right? Yeah. How big is it?
Nobody knows.
Nobody. Okay. Yeah. You don't have any.
I don't have
independent check. Okay.
Because of these correlation effects, so I cannot really precisely say what it is. It's a question actually I asked a theorist, asked them to help me to understand, but I haven't got the answer yet. Yeah. What's the number of G factors?
Okay. Maybe one last question. Yeah, you're next to Mike, but okay, please.
Yeah, so between mu equals -1 and mu equals -2, do you see any fractional states at all?
Sorry, I cannot hear you clearly. Yeah.
Do you see any fractional states between -1 and -2?
We haven't seen any fractional state. Yeah.
But it's the same band, just the opposite valley, right? So something else is going on.
We see a charge order state, but not the interesting fractional states. Yeah. So let's just go back to, it's here. So we see a state, but there's a charge ordered state. But not the non-billion or whatever other even denominator state people predict the electricity.
You see 2 minus 2/3, that's, I guess what I'm asking. Quite the exotic non-billion states.
2 minus 2/3.
2 minus 1/3.
We haven't seen any signature of that.
Yeah, okay.
Yeah.
Interesting.
But that matches two band per valley calculations. That matches band mixing calculations. Yeah.
Okay, so let's now thank Xiaodong again.
Thank you.